Oh, what the devil, there it is. Ruiz. Ruiz. Well, you are certainly the most feminine-looking Ruiz in the room. Where's Ruiz? And you're in seat 9?
I was sitting back there, but that's only because I came in late.
Yeah, well, did you not? Maybe we need to show that again. So.
Is that set in stone? Because I really don't want to sit there.
You really don't? Okay, well, Ruiz, if you would please, just go fight him for the seat that you signed up for. Why don't you go ahead and move someplace anyway so I can. You're welcome to sit anywhere somebody hasn't already been decided they'd like to sit there. And your name is? Getman. And you weren't here last week?
I was here. I just came in late. David did this.
Okay. All right. It's going to be a fun semester, I can already tell. Let me assign. Here we go. Get one. Well, the only reason I called on Ruiz is because he was yapping his mouth when I was trying to begin class. And so I was going to ask you what the answer to the problem was, but it turned out you were. Never mind. Never mind. All right. What do we got started on? What did I do? There we go. We got started on an introduction to the class. We got started on tributary loads for, I don't remember. What were the tributary loads for? I'll ask her in the back. That's the new lady. Vitito. No, Vitito. Well, no, you just came, didn't you? So it's not fair just to pick on you just because you're trying to get a date with the guy next to you there. Alan, were you here last time? No, you weren't here either. Hunter, were you here? No. All right. Why did we do tributary loads? Okay, we calculate how much loads flowed off, went to the beams and the girders, right? And then, of course, to the columns. And we took those areas, and we took all the load that was on top of those areas, and we moved them to the beams. And we took those beams, we let them put their feet on the girders, and the girders then had some loads, and then the girders actually load up the columns, but the tributary areas for the columns, we didn't fiddle following with from here to there to there to there. We just told each column halfway to your buddies is your fair share in both directions. Then we did some reduced loads. Why did we do some reduced loads? When did we get to reduce the loads? When did we get to reduce the loads? When, oh, never mind. When did we get to reduce the loads?
When there's a certain amount of square feet involved.
That's the trigger point, but it was only for one kind of loads. That's what I was thinking about. What kind of loads? Why not dead loads? It's a good start because
the dead loads are like just set in the line.
they're real. They're always there. There's no doubt about it. People loads, we don't know. A lot of times some people won't show up, or they'll show up late. You know? So they really won't be loading the floor like we think they'll be, especially if you have a great big class. And if you don't have assigned seatings, you watch. You know, I've been in that kind of class. Half the people are gone, so it's really easy on the beam. So you got to reduce the loads if they were live. All right. Now, we did wind loads. I got several comments on wind loads. So is there a theory behind the wind loads? Well, yeah, there really is. The people who did all this probably have tons of data and tons of equations that do all kinds of things, but it has to be put into some practical form for you to use. In other words, they can't show you all 9 pages of differential equations for nothing but gusts, except for the people who are doing the research and the guys that are considering changing the code because we need a little more or we need a little less or something like that. So it does boil down to a bunch of factors and being able to use them. You have a gust factor. You have an importance factor. You have. There's 15 of them. And there's tables of them, and you go pick out the one that really applies to you, and that's, as an engineer, what you do. If you see, gee, I thought engineers did sigmas equal to MC over I, where we had like an overall theory that told me what the stress in the beam was when it was bent. That's true, but bending of a beam is a very relatively simple thing, very straightforward. We can give you the controlling equation directly, and boom, you go. But when you get into things like wind loads and importance factors and all that stuff, there's not much you can do but take the results of 30 or 40 years worth of heavy-duty research who have put this stuff into tables. You go find out where you are in the United States. You saw that little map with the little contours on it that told you how much load to expect. It took people years to figure that map out and determine what was a good number in that area. And then the gusts, and then the importance, and then all of this other stuff that you saw. Same thing works on page 63. They have an equation for snow loads. Where the 7/10 come from? $250,000 worth of research, probably up around the north. Let's make them pay for it. We don't have any snow. Times C sub S, C sub B, C sub T, importance, and P on the ground. So you go find out basically in your area with a map like you saw for the wind, you go find out what the basic loading on the ground is. Probably not too hard to research it out. Probably it looks something like this, my guess. Every now and then they do find 80 pounds a square foot in Boston, but not enough to really be able to design for it. So they went ahead and picked 40 pounds a square foot in Boston. And that number's in the book. That's the only reason that I used it. Here, I'm sure it's 0. And then depending on the slope of the roof, if it's flat, it's a 1, and it goes lower as the roof slopes, as you might imagine. The snow slides off. An exposure factor. If you're behind a bunch of buildings, then when the wind blows, it probably won't settle on your roof. 7/10 if it's windy, 1.3 if it's sheltered. If there's a heated building, you get a factor, and you don't copy these down. For heaven's sakes, you can, I guess, but it's on page 63. 1.0 if it's heated, so they figure most of the buildings will be heated, and if yours is going to be a warehouse and nobody's going to be in there, they're going to make you bump up your loads by 20%, and then a factor based on importance. So there's some engineering stuff that we do like that feels like you're just pulling numbers out of tables. You understand where they came from, but that's about the best we can do to give you a design for snow load or a wind load. Now, a lot of this stuff in here, in chapter 4 starting, is stuff that, for heaven's sakes, you know how to do. And chapter 3. And I wouldn't know this except I just got through finished teaching half you guys statics, and I know that you know how to turn a uniform load, at least I certainly hope so, into an equivalent concentrated load. And for instance, when you see a 345 book that's got this in it, here's how you take a force and break it up into 2 components. I'm thinking that he must think that you haven't had statics yet, because I know you have. So a lot of this stuff I'll just mention very briefly, but we're not going to do a lot of this. We're going to hit this in a hurry. If I've got a truck and it's got a 30 kip wheel loading and a 30 kip wheel loading and a 50 kip wheel loading, and these dimensions are 8 feet and 30 feet, I don't think you should have any problem turning that into a single equivalent concentrated load. Now, those loadings would not produce the same bending moment in a beam as would their static equivalent load. But you get this equivalent load, for instance, to solve for reactions. You'll also find out where this load is located, so you can find out where to put these wheels to get the maximum bending moment in a beam. You'll use it for things like that. You call that point A. Those wheels have a tendency to roll about a point of your choice. And when you get through telling me that all of those could be replaced by a single load, 50, 6, 7, 8, 9, 10, 11, 110 kips, I would insist that the tendency to roll of the original set of wheels about a point of your choice should be the same for your equivalent load as for your original loads. So you would say that the sum of the moments about A is equal to minus 30 times 0 minus 30 times 8. That's a sign convention of your choice. Most people use a right-hand tendency to roll as a positive number. Minus 50 kips times 38 feet has to equal to the same when you lie about your loads to make your life easier, or to find out where to put these wheels, or for whatever purpose, should equal to minus 110 kips times where you intend to replace the loads as an equivalent concentrated load. And then you solve for X. And if you're already getting bored, that's good. I'm bored too. That's old stuff. Resultant of a distributed load. Probably in 210 you learned how to take some weird looking load that nobody had ever seen before. Y is equal to cosine X log of X divided by something, and take it into little bitty slices and find out the height and multiply X times dx and stuff like that. The loads that we normally use don't have those kind of looks to them, but it would certainly be necessary for you to be able to take something like that and tell me how much load is underneath it, and tell me where you could replace it with as an equivalent concentrated load. If this was 20 kips per foot, and that were 30 kips per foot, and this were 5 feet, 10 feet, 20 feet, then you should be able to break it down into little pieces that you fully understand. A triangle with a height of 10. You're going to take care of the 20 down here. And where he lives, his centroid. And another area, 20 times 10. And where he lives. And this area and his third point. And you should be able to replace that with a single equivalent concentrated load. Probably if you're really solving for reactions on a beam, it would not be worthwhile to turn that into an equivalent concentrated load and then put it on the beam to find the reactions. It would make a lot more sense just to go ahead and replace them individually by what they're equivalent to. Here's the first load. It's 20 kips per foot tall and 10 feet wide, so the area under that curve is 200 kip of load. Here's 220 kips per foot high times 10 feet wide. Feet cancels feet, leaves you with kips. It's 200 kips. And from the left-hand reaction, you'd put it where? Let's just pick somebody at random here. Getman. All right. No, that's okay. Well, now one thing, don't write too much. Anybody, really. I don't want you to write none if you need to, but these will be posted. So sketch down enough so you know where I'm at or something, but I know some students really do. They spend all of their processing power getting the figures and the equations and everything right, and then they go home and say, well, what the devil did he say? So I'm really asking you for this uniform load right here on this beam, where would you put that 200 kips? It's 20 by 10, so that's why we put 200 kips. Where would you put it?
It would be 10 feet from the front.
That is correct, and the reason he says that is because it's 5 feet to the edge and another 5 feet to the centroid of the shape you're discussing, and so that's 10 feet. Then this one you broke up into a triangle. You could, if you would rather, you could break those up into two triangles. In other words, a triangle on the bottom and a triangle on the top. I would not break it up into this shape here because I don't know where the centroid of that is. I can't just go stick it on the beam. So that would be 10 tall and 20 wide. 10 times 20 is 200. Somebody stole half of it. The area factor of a triangle is a half. The area factor of a parabola is a third. A parabola that looks like this. They don't really get much worse than that. So, is it 10 by 10? What did I say? 10 by 20? Thank you. I don't think I said that, but the only way you'll ever prove it is to go back and check the tape. But you're absolutely right. It's 10 tall and 10 wide, and that's 100. Somebody got half of it, half of 100. You're getting ready to put a force on here that says 50 kips. Then the question of where to put it.
Would be 2/3 of the way.
It would indeed, plus a little,
Plus the 5.
plus the initial 5 from the edge. That's right. That would be 5 plus 2/3 of 10. So that's 5 plus 6.67. There's no reason to write down 6.666666666 because they can't put it that close. They will if you write it on the plans. They'll also charge you several $1,000s to go out there and do it. Just tell them put it right around there, around 6 2/3 feet. Then finally we have this one. So you put the load on there, and it is 30 by 20. Cut in half, 30 by 10, that's 300 kips. And then where you put it, for summing moments, would be 15 plus 1/3 of 20. 15 plus 20 over 3. Here would be your reaction at A. Here would be your reaction at B. I probably wouldn't even bother showing you that. Goodness, hope you can do that. Do want to emphasize, once we start drawing shear and moment diagrams, do not draw a shear and moment diagram for this case. This is a total lie. The moments in this case here will be much greater than the moments with this load all nicely spread out. That's why if you ever see somebody walking across a very slender piece of wood and it starts really bending, you'll see them, they'll just naturally, they'll get lay down and they'll crawl across the thing. It's easier on the board. Yes, sir.
The bottom half of your
Oh, it's off the thing. Thank you. The word is hey. Okay? If you can't see it, just say hey. No sense in raising your hand or anything else. Just, I don't know immediately. Hey, what? Oh, yeah, I know what. Put it so you can see it. All right, so that covers like through page 79, page 80. Sometimes you will have rather complex distributions. Wind loadings on the sides of buildings, a lot of times they'll have a number, and then they'll have a number, and they'll have a number, and it's not linear, it's not parabolic, it's not anything. It's just, you remember these numbers, they came off of the factors with a H on them for the height. And they just draw straight lines in there, and they just go ahead and assume that probably you could just go ahead and take the average and stick it in the middle. It wouldn't be that far off. If you want to, you could go ahead and break it up into a triangle and put them at the third points. But we probably don't know the numbers that close anyway, and these things are usually pretty close together. Supports, he shows you all the supports. By now you surely know all the supports. Pins, rollers, stuff like that. You probably hadn't had a lot of practice with structures that have pins inside of the structure. So we could fiddle with those and you would probably be something reasonably new. Let's say, for example, I had a cantilever beam and it was pinned to another beam, and that beam had a support underneath it. I'd say you had a triangular load on this beam, 12 feet across or 12 meters across. And the load is 100 kilonewtons per meter. The dimension to this is 8 meters and 3 meters, plus a concentrated load on the end of 500 kilonewtons, and a concentrated moment. That concentrated moment probably came from a beam that was sitting like this. You see it's a wide flange. It actually goes down the road to the next one of these, and there's something sticking out of it that twisted it. Or it could be that at that point on the figure, I've got an electric motor. Once that motor accelerates, it causes a twisting moment or a torque, and that moment is equal to 1,000 kilonewton meters. And I would like to solve for all the reactions on that structure. Now that structure is statically determinate, and there are things in here, there's pages that attempt to tell you how to calculate how many, if it's statically determinate and if it's unstable or if it is more highly constrained such that they call it statically indeterminate. The truth is, I think you do just about as well and you make fewer mistakes rather than count the number of reactions and count the number of things they call special conditions, is just kind of take it apart in your head. This is a cantilever beam. You've seen them forever. Every time something's stuck out of a building and it's jammed into the bricks, it's a cantilever beam. It has the ability to resist that kind of a load, that kind of a load, and that kind of a load. It's just like a diving board. And if you take the whole structure apart, you've seen something that's stuck out of the wall like that, and it stands up just fine. Doesn't have a tendency to go anywhere. Now then, to that, I'm going to bring in a piece of steel, BCD. And if you just let it sit in the air like that, with only one support, you know what would happen. The same thing would happen with this pencil. Every time you do it, it's not stable. It falls off. So what we'll do is we'll pin it to something that is already stable, and we proved it's stable, and then that ought to sit still. It's just like a beam with a reaction at B and a reaction at C. And you could add as many more of those as you want, and sometimes they do. Sometimes there are several of them in a row. Yes, sir.
At the end of that second beam.
All right, do you mean this thing? It's like a wide flange. They look like this. They're used to carry loads from this piece of paper to the piece of paper that's behind this one, about 20 meters. And then every 20 meters there's another one of these things stuck out of the wall. And they connect them together so that you can walk on the top of them. In other words, the floor would go on the top of this.
So you're saying that goes into
This goes into the board. That's correct. All right. How do you solve such a problem? Thoughts?
you can start by calculating the concentrated load for that triangular.
You could. In other words, he says, before we go very far, you're going to have to replace the uniform load with an equivalent concentrated load. Otherwise, you're going to, when you sum moments, you're going to have every grain of sand times its own personal moment arm, and you're going to be here for years. So I agree. Take it apart is what I was thinking for first. And actually, everything that you said is right, has to all be done. First thing I think of is draw free bodies. And as you draw these free bodies, replacing these loads with equivalent loads makes a lot of sense. So the first thing is, I'd show you that this is a vertical, this is a horizontal, this is the moment about point A. Point B, I won't show you any forces because they're inside this structure. And then I would show you a reaction at C. It would be a vertical reaction only, no horizontal reaction. Reason being, it's a roller, which can't provide a horizontal force. And I'd look at it and I'd see if I could solve for it directly right now, immediately. 1, 2, 3, we have 4 unknowns. We have how many equations of statics? You have 3 equations of statics. So you're destined not to get an answer for all of them. Every now and then you can kind of cheat and one of the answers will come out. But even though you get it, you've used up one of your equations to solve for one unknown and you still have more unknowns than you have equations. So probably the smart thing to do is go ahead and start breaking it up. First off, I'm not going to show the wall because that was a little bit cheating to call this a free body with a wall on there, but I did show you the forces. I'd show you a horizontal, which I do not guarantee the direction. I have no idea. But I have to put an arrowhead on it, and I have to put a name on it so I can put it in the equations. I get students who say, well, why didn't you draw a free body? Well, I didn't know which way to put the forces because I thought they might be wrong, and then I would have a wrong answer. It's not going to happen. If you guess this arrowhead wrong, your equations will say minus. That'll tell you the arrowhead goes on the other end. Then you have an A vertical. This is a guessed direction. And then you have a moment at A, and this is a guessed direction. And then here we have a pin. In general, a pin can provide a horizontal force, and it can provide a vertical force. I'm going to assume that the vertical force goes down on this member AB, and I'm going to call it B vertical. And I'm going to assume this goes to the right, B horizontal. And then again, to make my life easy, I'll go ahead and follow the suggestion that I replace all of those bags of sand with a single concentrated load at the centroid of the figure. You'll notice I picked a better base, a better dimension on this one, 12 meters. That means this is 8 meters and 4 meters. And the amount of load is 100 times 12. That's 1,200. Half of it's missing, 600 kilonewtons worth of sand. Then we draw a free body for the other piece. Incidentally, by drawing this free body, you just added 3 equations to your set of equations. Sadly, you also added 2 unknowns that weren't on the first free body. Let's call this free body number 1. Let's call this free body number 2. Let me assure you that if you don't number the free bodies, and if you don't write down, hey, boss, I'm using free body 8. Equation number 13 is. If you don't do it in a logical order like that, he'll have no way of checking your work. All I can do when I give you a problem like this on an exam is if you don't show me which equation you're using and which free body you're using, I just look in the box. And if the answer is right, I say, great. I love those. They're easy to grade. And if it's wrong, it is wrong. That's a binary situation. Yes, no, minus nothing, minus 20. When you come in, you say, look at this. I have 4 pages of work. I only have 1 mistake. Yeah, but it's too late now. Tell me what you did. B horizontal is assumed to pull on member AB. Which way must I show it on the other member? The other way? Well, I'm not sure I understand. I'm going to do that, but then I need an explanation for it from you. When you drew another free body here, now you're telling me the arrowheads should oppose. In other words, if this one's shown to the right, guessed to the right on this, then the guess is to the left on this. But when you showed this one up, when you redrew the free body, you still showed it up. So I don't understand. Here's two free bodies, up and up. Here's two free bodies, right and left. Something's going on here. What?
Depends on the other.
True, that's how come they have to be opposing each other. But when you drew this free body, how come this one was up? Why didn't you show that one down?
We just redrew the
Exactly. It's a Xerox. In other words, when you showed me this piece of steel right here, on piece of steel AB, you guessed this reaction was up. All you did was Xerox it. All you did was you just redrew it. It's the same piece of steel. These are the same forces. So they go the same way because they're the same piece of steel. On this one, on the other hand, when you guessed B horizontal in tension on the right end of member AB, you said it is pulling. When you moved to the other, and there's the trigger, when you move to the other piece of steel, you have to show it the other way. And if you forget to do that, you'll get all kinds of wrong answers. If you ever find out this arrowhead is wrong in one of your equations, you must immediately go change this arrowhead because it's wrong also. Since you guessed that someone has put their feet down on the end of this member, you have to show me what that member is doing to your feet, namely pushing up on your feet, be vertical. Now then, this thing right here must be shown true or false. Other words, must be shown appropriate or not. Yes, they are. Why must this be shown up? Because on this free body, you guessed that force up on this piece of steel. This is that same piece of steel, and therefore the force is, again, up on that piece of steel. Then we replace any uniform loads or distributed loads with an equivalent concentrated load. In this case, we don't have any. 1,500. And 1,000. Question? 500. I don't know why. I just wanted more load. Thank you. Because it says 1,500. Okay? And if you see that, you know, even if it doesn't matter, if you say, okay, well, I know what he means, holler. Because the guy next to you won't, and he'll call me at about 12 o'clock at night trying to figure out why that thing says 1,500.
So
Now,
that you have there really doesn't change your analysis.
oh, well, no, it really did. I was just trying to show you something that caused this moment. But let me take it off because it's obviously confusing. I was just trying to show you how you get such a thing. Probably because some other piece of steel frames in from an angle which is being twisted and puts a twist, a torque, a moment on the end of that member. All right, so now we have our free bodies. As soon as they have dimensions, I guess they're free bodies. 8 meters. The dimensions are already up at the top. And the dimensions up at the top, 8 meters and 3 meters. Now we have free body 1, free body 2, free body 3. I just really do absolutely insist you tell me what free body you have decided to go tinker with and write down, this is equation 1 using that free body. Using Which free body would you like to start with? 3. All right, let me see why you didn't say. First off, I know you didn't start with 1, because we already looked at 1 and had too many unknowns to get started. Looking at free body 2, you have 1, 2, 3, 4, forget that, 5 unknowns. Over here you have 1, 2, 3 unknowns, so that's a good bet. And therefore, it's probably going to be able to get started on free body number 3. Using free body number 3, my first equation reads, what's the most powerful equation you have? Sum of the moments. Pick a good point to sum moments about, and you'll wipe out all kinds of unknowns. Sum of the moments about B is the one that comes to mind first. The truth is, were you to sum moments about C, B horizontal would have no moment arm, and the reaction at C would have no moment arm, so that also would be acceptable. Using free body number 3, I'm going to sum moments about B equals 0 is equal to minus 500 times 11 meters minus 1,000 times what? Times 11? That's right. This is 500 kilonewtons times 11 meters. The units are kilonewton meters. This is 1,000. It's already a kilonewton meter. Were you to put a moment arm on top of a thing that's already a moment, you'd have a kilonewton meter. Well, nobody knows what a kilonewton meter even is. It is a moment. It's ready to go in this equation. Plus the reaction at C times its moment arm, 8 meters. If you don't see why I'm doing those pluses and why I'm doing those minuses, you need to go practice. And therefore, somebody with a calculator, give me a hand here. Reaction at C is equal to 500? You're kidding. Right on the money? No? What'd you get?
We got 6,500 over 8. I don't know the calculator.
Okay. 812.5, all right. Maybe I just misheard. Kilonewtons, because being something even when you put so many weird numbers in there like that is pretty low probability. As soon as you get an answer, I'd recommend you go put it in there. If it came out with a minus sign in front of it, I would expect you to immediately look around, make sure nobody's watching, erase that arrowhead and put it on the correct end, erase that arrowhead and put it on the correct end, and then rewrite your equation right quick. There'll just be a few minuses will change to plus or vice versa. No one will ever know you're less than a perfect arrowhead guesser. The real purpose, of course, is if you leave the arrowhead in that direction and write down a minus 812, they may notice the minus and they may not. And you may notice the minus and you may not next time you use it in an equation. The chances are pretty good that you'll miss the fact the arrowhead is the other way. Came out a positive, therefore we leave the arrowhead alone. 812.5 kilonewtons. List it twice. Anytime you get an answer, there ought to be 2 free bodies on which that answer can be listed. There ought to also be 2 arrowheads that need to be left alone or need to be changed. Now, I think once you get that free body going, you ought to just keep on beating it as long as it'll cough up more answers. When it won't cough up any more answers, well, then you move on to another free body. Equation 2. Marino, give me another equation that will give me something in the free body number 3. That's correct. And the way he knows that is he looks across here and he says, I know that up and down. I know that up and down. I don't know this up and down. He puts one finger out. And then he says, okay, there's only one unknown in the sum of the forces vertical equation. And I'll leave it under, using free body number 3, sum of the forces in the vertical direction is equal to 0 is equal to plus B vertical plus the reaction at C, which is 812.5 minus 500. And that's all of them, and you solve for B vertical, and being careful with the sign. If you leave B vertical on this side of the equation, then the 812 comes over as a minus. The 500 comes over as a plus. That means I'm going to get a minus for an answer. What'd you get? 312.5, thank you, kilonewtons. I would immediately, personally, it's up to you. I wouldn't even write an answer on it. I'd go find one arrowhead and I would change it. I never write in ink. I learned that many years ago. And I change it twice. And I'll put the arrowhead on that end. A minus with the arrowhead left alone is just as accurate, is just as true, but it is just not as noticeable. Then I would say sum forces vertical is equal to so-and-so is equal to, I'd say, minus B vertical. And then I would change this minus to a plus. And I think that's all I need to do. B vertical moves over as a plus. It's equal to a plus minus plus 312. Now I'll go list the answer on the free body. 312.5 kilonewtons. And list it twice, 312.5 kilonewtons. Now the only reason I do this is because I don't think there's any reason in the world for me to show you how to get reactions on a simply supported beam. I don't think there's any reason in the world for me to show you how to get reactions on a simply supported beam with overhang. But when they get kind of strange like this, then you probably haven't practiced with these and probably may be less familiar with them. I probably might say we might work one of these someday. Thank you. Hey, what? Here's the support, and here's the support. Well, one of those is relatively unusual. That's not the stock in trade when you took statics or even when you took 305. Finishing this one would say equation 3, but it's worked the same way exactly. If you see a pin, you put in a force, and you put in a force, and you know they may be wrong. And here you see a roller which goes that way, so you put in a force right back there. Those are your reactions. You have the same equations of statics as you had always, and you solve for the forces inside there. Sometimes there are really too many forces. For instance, I can easily make this what they call statically indeterminate by tying it down too many times. And usually you can tell how many degrees indeterminate something is. First thing, if you worry about if it's indeterminate, you just start taking stuff loose. Once it falls down, you say, whoops, that was too many. And you put one back on it. And after you put that one back on it and you look around and the boss says, oh, well, there's another one because that's not a roller there, that's a pin, then you know it is 1 degree statically indeterminate. Every time you take something that's nice and stable and sits still and is statically determinate and add a constraint to it, don't let him move where he might like to. You're adding a degree of indeterminacy to the structure. Equation 3 would say some forces horizontal is equal to 0 is equal to minus B horizontal. And that means B horizontal is 0, and it's in the wrong direction. But it's so tiny I don't care. It's equal to 0. It's equal to 0. Now that I'm ready to move to another free body and start picking off things. Hunter, what free body would you go to next? to, I can't think of anything funny to say, to solve for some unknowns. Well, a fair question, I guess. Anything I don't know would be really what I'm looking for. So number 2 would be fine. I believe that also you could go to this one here and you could also get answers out of this one now. And half of you will go here and half of you will go here, and that's perfectly okay. It wouldn't make any difference which one you went to, as long as you tell me where you're going. I'm using free body number 2. And I'll write down the equations that I would use in order, and then I'll let you do the work on your own. My 4th equation would be, almost always the thing I'll do first is sum moments. It's the most powerful equation I've got. I probably will pick point A. Maybe I will write that equation down just to make sure everybody sees it. If you sum moments about point A, the equation reads sum of the moments about point A is equal to 0. Why? Because it's what? Because it is statics, that's right, because it's supposed to sit still. It will not be 0 on an airplane. It'll be a propeller and it'll be moving like crazy. But in this class, all our things sit still. Therefore, the sum of the moments is equal to mass times acceleration. There's no acceleration. It's equal to 0. Is equal to plus m sub a. This is still using right-hand rule for the direction. And I've guessed it's this direction, so I'm going to call it a plus. Minus 600 kilonewtons times his moment arm of 8 meters. Plus 312.5 kilonewtons times his moment arm, 12 meters. I don't remember in our homework, does he do, you've already worked a lot of homework, has he got any meters in there, or does he just do everything in feet? Yes, some meters? All right, so we'll try and mix them up also. There's one equation and one unknown. And so you'll solve for m sub a. Your next equation would say sum of the forces vertical is equal to 0. And your last equation would say sum of the forces horizontal is equal to 0. And solve for all the unknowns. Now that was one of the problems you were having on some of the homework we had this time. I don't remember which one it was. But you had to break, I guess it was that piston rod thing. You had to draw a free body of the whole thing. And you had to put forces on it. Many of you had the piston in there, and you had, maybe so, thank you. Good point. Glad you told me, because I'd have sat there and worked the whole problem. All of your classmates are looking at you ugly now. Come on, don't tell him when he goes off on a tangent. Let him go. Good point. You do need to be able to break these things into pieces a lot of times to get enough equations to solve for them. All right. And he talks about free body diagrams in the text. It gives you your equations of equilibrium. This would make a good 221 text. Got some good examples. Got one that looks very similar to the one you and I just did on page 95. Now, let me show you some beams. Here's a beam, and here's the load on it. What do you have to say about that beam? It's floating. No, it's not. There you go. Now then, let's see if you think it's floating. No, you don't think it's floating. It is not stable. And here you are, right there. Therefore, you need to put some supports on it. So let's put a pin. Well, that's better than it was, but now it still rotates clockwise. And so let's put a roller. And you've seen hundreds of those in your problems, and you've seen hundreds of those every time you went under a bridge. And you know it is statically stable, and you can solve for the reactions from statics. Yes, sir.
I have a question. If beams are really good in compression, and I guess tension also, and not so good in moment?
No, let me revise those words a little bit, okay? Beams are extremely strong in compression, because the stresses in compression, if you have a compressive force on them, every little fiber takes an equal amount of load or stress. On the other hand, when you bend something with a bending moment, the top goes into compression, or vice versa. The bottom goes into tension. This guy here don't know what to do. He looks at the guy at the top. He says, he tells me I should go compression. But if I look down here, the guy says I should go into tension. So the stressors are distributed like that. You see all these fibers in here that aren't really working their little hearts out for you? So your real words, I would prefer to say, beams or pieces of steel are extremely strong in compression, and it's a lot harder if you bend them. So go ahead.
So if that's the case, why do people usually put support on one end and a roller on the other? Because that would allow the beam to kind of deform under in like that sort of way.
Right. So is your suggestion though that we put a pin on both ends?
Yeah, because then when it tries to deform, it'll kind of.
It would help support the beam slightly. The problem is these things. What you're talking about here. Once this beam deflects, this piece of steel is going to get a little shorter. It's going to go a little longer route, and they're going to put tremendous horizontal loads into these pin connections, and we can't stand that. It's really difficult to come up with that. But a worse thing than that is, once this thing gets hot by 100 degrees, it is going to get 0.06 inches longer. There's nothing hardly you could build that's going to stop it. You could say, well, I'll put it between two solid concrete walls. When you come back tomorrow, when it's cool again, you'll find a little H-shaped hole punched in the wall. It's just tough to stop them from getting longer. And therefore, due to temperature loads, it'll tear this thing out. I don't know if you're probably too young to even know or remember the Hyatt Regency collapse, had a walkway collapse. That was the second failure in that building. That one cost them something like, I don't know, a couple of $100 million to pay for all the dead people. But about 2 months before that, they had a roof that was built like you say. They jammed both ends into the wall, and they had steel rebars stuck in the wall, and they had steel rebars stuck in the wall. Had they been able to get the roof on it and heat it up, they'd have probably been okay. But the coldest night on record, I believe they told me, came through and the roof was still not on it. It was about half on it, so it means there was cold air all around it. This thing got shorter by about a half an inch. It just tore it right out of the wall and dropped one end into the mezzanine floor. So that's not a good idea. Now, the other thing is I've been asked before is, well, why don't we just put a roller on both ends? Then you won't have to worry about thermal stresses at all. Somebody will steal it. So put a pin, put a roller. All right, now then, let me put another support, because what I find is that this dimension of 100 or 60 meters is doable, but the stresses in the beam are relatively high unless I make it a very, very deep beam. And I prefer not to have to spend that much for the beam. So what I do is I come and stick, well, let me show you the deflected shape first. This is the deflected shape. Should be symmetric, of course. No, it shouldn't be symmetric because the load is to the left. So my pencil knew what I was doing. It's just I didn't. So what I do is I come in, because this deflection is large, and even then I have to have used such an expensive beam that the architect has a fit. He says, well, I wanted 180 feet of clearance in there. He says, but if you really need a $500,000 girder in there to do the job, I think I'll go ahead and accept a column in the middle. I say, good idea. So we put another support in the middle or someplace. The beam now deflects, but it now must go back through point 0 deflection. And that means this side would actually raise up slightly. Of course, that's unbelievably exaggerated. If a beam ever deflected that much while you were on it, you would immediately leave. But it can easily be like a half an inch. But you have now made this structure what we call statically indeterminate, because you've added a support that you didn't need from statics in order to get answers. And you did it for a purpose. The purpose you did it for was to reduce the span from 60 to 30 meters, and now then the beam might well only have to weigh maybe a third as much as it used to. I believe the equation for max moment on a uniformly loaded beam is WL squared over 8 or something like that. That L squared, that's a powerful factor in calculating moments in a beam. And every time you do so, you restrain it again. And let me quit restraining that one and go ahead and restrain another one here. You only needed one on each end, or you could have just had these two. That would have worked. You and I just got through working with a beam that looked very similar to that. Had a support and a support, and there was a piece hanging out. But if you assume that the original structure was end to end, and you put in 3 additional supports, that is 3 degrees of statical indeterminacy you've added to the beam. Now, if you can't get enough equations of statics to do the job, you're going to have to get some kind of equation from someplace else. You can look in a book, you can pray, you can do whatever you want to do, but you need another equation. Well, the equation is what they call a compatibility equation. Used to be this beam was permitted to deflect as it desired. You now make it compatible with this new reaction, namely it has no deflection at that point. In this one, probably the deflection would be kind of down, come in, it might have a little bit of rotation here, but the rotation is not prevented, and then it would be down, and then it'll go up, and then it'll go down, and then it'll go up. You can get a piece of a coat hanger, and you can support it at these points, and you can push on it with your hand. You can see how it deflects. That's pretty much how the beam will deflect. If this right here turned out to be an inch, more than likely this would turn out a 1/4 inch, and more than likely this one would turn out to be 0.05 inches. It quickly damps out, but that's the general shape of the beam. Let's say you had a structure that looks like this. First off, if you support it like this, and you ought to start getting a feel for this. I mean, you really should. Is it okay? Is it going to stand there? Yeah, it is. It's just like a diving board that someone bent. And you can stand on it any place and it will, as long as you don't overstress it and it doesn't fail, it will be fine. And so if you decide to add any new supports for any purpose whatsoever, you are adding degrees of indeterminacy to the structure. So if I do this to the structure, how many degrees indeterminate is it? Well, I heard every number from 1 to 3. Would someone like to put out a 4? No? Okay. It is 1 degree indeterminate, 2 degrees indeterminate, 3 degrees indeterminate. The real way they analyze that structure, or at least one way they do, is to say, that's nonsense. I'm going to have the structure all tied down like that. There's the original structure, and they'll put the original loads on it. Perhaps the original load was nothing but that, and maybe also a uniform load. And they will say, this is what I want. And the guy who's designing it in steel says, I don't think that's really what you want. This is going to be a 42 by 900 wide flange. What is a 42 by 900 wide flange? Should have learned that in 305. Who giggled? He's up. Everybody point at him. Boy, what an honest guy. He raises his own hand. Makes me feel bad. Should have learned that in 305. As again, I know half of you know and just won't volunteer, so I'll just have to go find some poor sucker and pick somebody at random. Getman.
It's a wide flange that's 42 by 900.
It's 42 is by 42 is right. It's 42 inches deep. It's approximately 42 series could range anywhere from 40 to 45 inches deep. They all started out 42, but as they roll different thicknesses, they roll different flange thicknesses and stuff. I don't even know if they make them in the 42s or not. Most books don't go that high. I think they go up to maybe 36s in most books. And what does the 900 mean? It's not the length, because then this is actually a real shape that you can look in the book and he'll tell you the moment of inertia, he'll tell you the cross-sectional area, he'll tell you the web thickness, the flange thickness. But it's the weight per foot. So this thing is about 42 inches deep, and the amount of steel in it, so I'm going to put about 42 inches. It's in that series. And if you were to cut off a 1 foot piece, it would weigh, where's the other line? There it is. It would weigh 900 pounds, right on the money. So when I've been told it's a 42 by 900, which costs like $900 a foot, I say, well, okay, maybe we want to tie that rascal down some more times. I release it to analyze it still. I admit I'm going to do this. They then find out how much that structure moves to the right and left. That's undesired. They will end up going and getting a hydraulic jack and pushing it back so that this deformation disappears. It bends down. This is delta. Let's call this ABC. This is the deflection at B in the horizontal direction. Here is some undesired deflection at B in the vertical direction. And they find out how much rotation, theta at B in the vertical direction, and they make it disappear. They very carefully push on it this way, and roll it like that. And actually, each of these interacts with each other. As you push it up, you get rid of some of the theta. As you push it up, you cause some of this to go away. So it's a very careful mix of those three numbers, which will make this structure bend like this. This probably bends down because of that load. How do you want me to deflect the structure right here? What do you want me to do with it? None at all. I want to bring it straight into the wall because that's what a fix is. So it would look like that. Let me draw you centerline distortions. Probably looks like that. Then this probably kicks out and it comes back in straight up and down. But the main thing this chapter wants you to do is find out how many degrees indeterminate something is. So you have a feel for how many equations you'll need to generate, consistent distortion equations, compatibility equations to complement your statics equations to get an answer. So I have something that looks like this, and it has a pin, and it looks like that, and it has a pin, and it looks like that. And it's supported here, and it is supported here. Will it stand up? You see how this thing right here is just going to roll down, not have any moment at this point. This piece is going to fall down with it, and then this piece here is going to roll over. It's not stable. It was stable before you put those pins in there. How many pins did you put in there? 2. You're going to have to come up with 2 more supports to replace the fact that you destroyed the moment at these 2 places in a statically determinate, what used to be, beam. So let me put one here. Now then I see that this left-hand beam is good and solid. I can grab on it anywhere and I can move it around. I can pull up on it to tie off my helium balloon if I want to. If you say, well, no, you can't because these little wheels will lift off. This is a convenience only. It's just a quick way to draw a roller support. If you have a downward pressure on this support, what they really do is they'll just take like a concrete beam, and here is the big old chunk of concrete on which it sits, and they'll put a piece of neoprene in there. It doesn't even have any rollers. And when the concrete beam wants to get a little longer, the piece of neoprene just kind of shears with the beam such that there's no horizontal force in there. If you're going to really have tension on the beam, then I'll have to tie it down. Probably the way I'd tie it down, this is the beam A, B, C. At point B, I'd come in here. Here's the wide flange. Here's the wide flange as seen from the side. I'd go ahead and cut this out. Cut out the flange. And then I would put a pin. If I can draw it in 3 dimensions, I'll try. I'll put a pin like that to permit the thing to roll left and right. And then on this one right here, I'll put a plate behind it. I'll drill a hole and put a bolt through there, or a pin. I'll drill a hole through here and bolt it to the web. This piece right here will be welded to a plate. And that plate will sit on top of the piece of concrete. Well, that didn't work out well. That's a contracting error. And we will put bolts down into the concrete, and we'll put hooks on the end of them so that the tension can be accepted into the concrete and then all the way down to the ground. So here's your beam right here. I'll make that thing be able to take tension. This is just a quick way to show what took 3 minutes to draw here. But I still have this problem. This is a simply supported beam. On the left end, it's supported by a good support. Come in here and pull up and down. This beam won't move. But there was a simply supported beam, and you added a moment in the middle, and I can't live with that. You can't just come in there and put a pin in my beams, and therefore I need another support. Probably you get away with putting another one here. This is the real problem. This is the real problem with using the equations. The equations count number of reactions, number of special conditions, number of this, number of that. But once you finish counting, you can still be in trouble. I mean, you guys very seldom build things like this. You usually build buildings or you build bridges, and you don't put pins in the middle, you know, unless it looks something like this. In this case, that works. That'll work right there by adding this to take care of the fact you took out that moment. You have a simply supported beam with a little cantilever piece to it, which is nice and stable. It can't roll left and right because it bumps into these pieces, and those horizontal loads go into this reaction. And this little piece here is supported on his left end like a simply supported beam, and this guy supports the right end, so that's okay. If you were to take this and put it, let me see if this works. Sometimes, no, that would still work. It's all right if you put the support there. And the reason being this, you take a look at this and you say, I'm not sure I like this. This little piece might roll clockwise. The other piece can't roll clockwise because it bumps up against this pin, and this cantilever beam will take up and down load, so this piece won't move. And since this piece won't move, this pin won't move, and that piece is supported. Every now and then you can get a combination of things put together where when you count reactions and count numbers of this, that, and the other, the pieces form a link and they can roll on you. That's why I think it's probably just about as good to look at it, see what you've done to it, and count, figure out whether or not it's going to sit still. Yes, sir.
So right now, this beam has no degrees of indeterminacy.
It has no degrees of indeterminacy. What would happen if I were to add one more support?
1 degree?
It's 1 degree statically indeterminate. That's correct. All right, does everybody think it's time to go? Gitman seems like he's already gone. All right. Shouldn't take any more than a minute, and by my watch you got 2. Solve for the reactions at A and B. And if you say, well, my goodness, why didn't you just ask me to write down my name? Well, that's about all this is. Check and roll. Solve for the reactions. If you didn't bring a calculator, I'm sure the guy next to you will lease one to you. Please do sit wherever you told me you were going to. If you sit someplace else, I think you're not here.